Good afternoon, good morning, good evening. Hello, everybody. I'm Rob Fisher, Head of Sales and Marketing on the optics.org website. And I want to thank you all for attending today's webinar on low latency imaging for next-gen mid-circuit quantum measurements. I am here with Dr. Ramon Smuk and also Dr. Sebastian Beer. First of all, I'll make a point of introducing our two presenters and also run through just a few house rules with regards to today's presentations. Now, we will have a Q&A at the end of today's presentation, so if there are any questions that you have for either of our presenters, then please do put them into the chat box and we will try and get through as many questions as we possibly can. If for any reason we don't answer your question, don't worry, someone from either Quantum Machines or Hamamatsu will get back to you directly. Okay. So first of all, I'd like to make a point of introducing our presenters. Today we have, like I say, Dr. Ramon Smuk, who is currently product manager at Quantum Machines, where he leads solutions for the atomic, molecular, and optical market. Previously, he worked as a research scientist at Muquans, focusing on design and development of atomic clocks. Now, he earned his PhD in 2015 from the Paris Observatory. Good afternoon, Ramon.
Good afternoon. Nice being here.
And I'd also like to introduce Dr. Sebastian Beer. Sebastian is the applications specialist for Hamamatsu Photonics. Dr. Beer has a background in biomedical engineering at Hamamatsu Photonics. He acts as the European camera specialist and is deeply involved in the emerging applications of QCMOS technology. Hi there, Sebastian.
Hi, everybody.
Okay, the first thing I'm going to do is transfer over presenter mode to Ramon, and then I am going to disappear for a few minutes for the presentation, and I hope to see you all for the Q&A at the end. So, okay.
All right. Thank you, Robert. So I'm going to share my screen. I hope everyone can see that. Yeah. So I guess my screen is visible. So today we'll talk about, as the title suggests, low latency imaging for next-gen mid-circuit quantum measurements. And we will focus on mainly atom-based quantum processors, but in general, this is an application that can be applied to any optically addressed qubit, any quantum memory that is being read out using cameras. So let's go right to it. I will start with a short presentation of quantum machines. So Quantum Machines, we are a company that is now 6 years old. We have a customer base of more than 300 customers, and we are more than 160 quantum physicists and engineers. We are regularly appearing in leading publications such as Nature Physics and Nature Science. And the whole company's kind of raison d'etre is to provide control solution for entities that wish to drive and read out qubits. So we really focus on quantum information processing, electronics for quantum information processing. And before we go into the details of this discussion, interfacing to cameras for mid-circuit readout, I'd like to do a short recap of our basic technology. First, I'd like to also mention that we are a company composed of about 25% physicists and the rest being engineers and sales and other other people. So we are really a company that builds equipment for physicists by physicists, and we are entirely focused on quantum control, and we have kind of the expertise to back that up, that claim. So what do we do at Quantum Machines? The basic idea is that we have what we call the quantum orchestration platform, which is a processor-based approach to quantum control. So what do we mean by that? We mean that we have these instruments called the OPX, in this case the OPX 1000, the scalar version, and these are basically a collection of DACs and ADCs that produce analog signals and read out analog signals going to and coming from qubits. Behind these signal front-end, this analog front-end, these DACs and ADCs, there is an FPGA-based processor, on top of which we have implemented our own chip architecture. So what we call our pulse processing unit. And this pulse processing unit is built up of several cores that all do the same thing. It's a collection of several operations, which I will flash them here. And so each and every core, basically each and every channel in this stackable platform of signals allows you to do several things. First of all, the signals that are being sent to the qubits are in general synthesized on the fly. So there's no need to, you can store predetermined waveforms in some memory and just play back them on demand. But that's, in the general case, that's not sufficient. So what we have is really numerical oscillators inside the pulse processor that allows us to modify signals on the fly based on feedback. So we can change the frequency, the phase, the amplitude, the duration of signals based on feedback, based on measurements that we've done only a few hundreds of nanoseconds earlier. And by doing so, affect the driving signals sent to these qubits. We also have waveform acquisition, and this presentation basically augments that and adds cameras to the kind of data that we can acquire mid-circuit. So you basically define in the sequence that you write in QA. QA is our own programming language that you then put on the pulse processor. You define some signals that you will play, and then some acquisition windows that will be opened in deterministic timing, and then the raw data that you acquire from in these acquisition windows will be analyzed in real time, also in the pulse processor, to extract information that can later be used to synthesize new waveform or to do branching and real-time processing, which are the other two things that the pulse processor can do. So we have real-time processing, we can do general arithmetics, we have a whole math library, and we also have control flow. So if then, for loops, while loops, switch case, anything you would expect to find in a high-level programming language, we have in QA, and this code, your program, your sequence never leaves the pulse processor. So there's no need to communicate in general with other computers or instruments in order to kind of close the loop. And so and this is a general framework for driving qubits. It doesn't really matter what kind of qubit you have. We are qubit agnostic at Quantum Machines, as evidenced by the fact that we have multiple customers doing, for example, superconducting qubits, spin qubits, atoms, ions, NV centers, and so on and so forth. So we have really a family of qubit modalities that we are serving. And we are really qubit agnostic, because in general every qubit is basically a two-level system, and the way that they differ from one another is only by the carrier frequency that is used to drive them or read them. And so a superconducting qubit, for example, could be at between 4 and 8 gigahertz, and an atom qubit is typically on the carrier is typically on the order of several hundred terahertz. But that doesn't change the baseband information that is being sent and received. And so that's how the same control platform that we've built is used for all qubit modalities. And so we are, as I said, qubit agnostic, but this, and we serve all these kind of qubit modalities. But this talk is focused on a particular family, subfamily of that, and these are the optically addressed qubits. So atoms, ions, defect centers, and so on. And what's special about these qubits is that they are typically imaged with light, either with cameras or with photodiodes. And this whole presentation, this whole seminar is about how can you incorporate cameras, in particular Hamamatsu cameras that we will see are the fastest on the market, as part of a mid-circuit low latency feedback sequence that allows you to do the things that are required from these qubits. So why focus on optically addressed qubits? Why focus on atoms? So that's kind of my role within Quantum Machines. So there's several reasons for that. We like atoms because it's a leading qubit modality. So here you see on the left, for example, this demonstration by Quera, where every pixel here, every white dot is a single atom, and they really exquisitely manage to arrange them in real time and create this little Mario movie. But this is here only to demonstrate how scalable this platform is. In the next slide, I will show you how people have already managed to arrange several thousand atoms. Orders of magnitude more than what is typically found in solid state qubits, so superconducting or spin qubits, what people typically associate with quantum computers, down dilution fridges. So this is not at all these kind of setups, but there is really an envisionable path towards having 10,000 and even more in qubits, which is something that most qubit modalities cannot really say at this moment. So scalability, to me, really, the atom arrays are currently the kings of scalability, and together with high fidelity operations, which was also a must. So 99.7% fidelity for 2-qubit operations was demonstrated. Single qubit operations are even better, and these are fast gates. So comparable to the time scales of solid state qubits, which are also on the order of tens or hundreds of nanoseconds. These time scales can be done with atoms as well. Reasonable laser power is sufficient to drive these atoms at these speeds, and also together with very long coherence times, certainly compared to solid state qubits. So atoms, it depends on the atom and on the systems, of course, and how well you arrange the kind of environment. But coherence times on the orders of hundreds of milliseconds are typical for these setups, and so you can squeeze really a lot of gates within kind of the coherence time of these qubits. So they are very long living, and that gives a lot of advantage. There's also the possibility to perform multi-qubit gates. So you can drive these atoms with a wide beam, laser beam, that drives not only the atom but also the adjacent neighbors. And you can people are working on having multi-qubit gates, not only 2-qubit gates, and that will allow you, if successful, to build up entanglement much faster than with normal techniques, than with just relying on 2-qubit gates. And in addition, the path to quantum error correction for atom arrays looks very promising for two reasons. One is this just abundance of qubits that one has, these many thousands. I will show you in the next slide. And the second is the fact that you can move these atoms around. And so maybe we will move to the next slide, where we can see here in the central pane the last demonstration by the Lukin group at Harvard, where again each dot here is a single atom, and they are moved around, dancing around, and when the two atoms get close to one another, you can see in the movie that the screen kind of flashes. That's the gate. Whenever you have this red circle between two adjacent atoms, that's when you apply a gate between two different atoms. Atoms need to be physically close to one another in order to apply these gates. We won't go into the physics of that. We won't have time for that. But the fact that these atoms can be moved around gives you an extra ability, extra connectivity compared to solid state qubits, which are typically printed on a chip, and you can only drive 2-qubit gates between adjacent neighbors in a surface of qubits. Here, since the atoms can move, they can skip an atom or two, and you can in principle implement any-to-any atom connectivity. The same goes for ions that we see here on the left. And that, it turns out, gives you a great advantage when trying to do quantum error correction, which we won't go into the details of in this discussion. But quantum error correction is basically the ability to take several such qubits, typically hundreds to thousands of such individual qubits, physical qubits, and transform them into a single logical entity that protects the state for longer time and reduces the error associated with these gate operations. And that's kind of perceived to being the way forward for quantum computing, taking collections of physical qubits and arranging them into logical qubits. And one very important figure of merit in this respect is kind of the physical overhead what people call the physical overhead, which is how many physical qubits, how many atoms in this case do you need to implement a single logical qubit. And it turns out that if your qubits can move around, or more precisely, if you can implement more than nearest neighbor connectivity, this overhead is greatly reduced, probably by close to an order of magnitude. So where one would need maybe with today's fidelities, with today's precision of operations in solid state qubits, one typically would need more than 1,000 qubits to physical qubits to implement a single logical qubit. With atoms, people think that the number is about an order of magnitude less. So you not only do you have much more atoms, you also have a better scalability towards logical qubits. So, and on the right here, you see kind of the current world record for the number of atoms. You see 6,100 atoms performed by the Manuel Enders group at Caltech. And these atoms, so this is a preliminary demonstration. Each one was shown to be coherent, but they are not yet a tightly packed array. So as you see in the movie in the middle, you need to arrange these atoms into an ordered array. There can be no defects between adjacent atoms because the 2-qubit operations are sensitive to the distance between atoms. So you must have all these 6,000 atoms basically collapsed and compressed into kind of a tightly packed grid. In total, there are 12,000 sites here on the right and only 6,000 atoms, because the way that this is done initially is you start by having, in this case, 12,000 traps, and you throw in them just atoms, cold atoms, and there is a probability of only 50% for an atom to be successfully trapped by these traps. And so in the end, you're left with about 50% of the atoms. 50% of the sites populated by an atom. So if you started with 12,000 sites, you will typically end up with around 6,000 atoms, which can later become qubits. So there's an extra step here when doing quantum computers with atoms, and all the same almost applies to ions. You need to shuttle them around. You need to move them around. The way this is done is that you project static trap, these 12,000 traps, with some holographic techniques, and these traps don't move anywhere. And that's where you place your initial kind of ensemble reservoir of atoms. And then on top of that, you superimpose dynamical tweezers. So again, laser beams that can pick up an atom and move it to a separate site on this grid. And these two dynamical tweezers, this is something that quantum machines does provide the signals for. So we do the atom arrangement. We have our own code to do that, but you can of course develop your own. And this will be kind of the first demonstration that we will show of real-time feedback with cameras. Since you need to take a picture of the atoms, know where they are, and then based on that kind of synthesize the signals that are moving these tweezers around to generate these traps. Just to recap a little bit, to control a neutral atom QPU, you need to go through a list of steps. First, you need to cool your atoms to prepare kind of a reservoir of cold enough atoms so that they can be trapped in these static traps, these 12,000 traps. You need to be cold because the traps are quite shallow. And then you need to do what I call instantiation. You need to move them around to create a tightly packed array. And then you can apply coherent gate operations. You can drive these qubits again with laser beams. This is out of scope for this discussion. This is also a challenge, and this also requires scaling. And the readout also is something that you need to do mid-circuit, not only for the instantiation, not only to see where the atoms are and to make them nicely packed, but also as part of the readout, as part of the sequence, part of quantum error correction, in the part of the things that are required in order to transform many physical qubits into one logical qubit, is to continuously measure these qubits and apply corrections to them. And that's how you kind of extract the noise from the system. So it's a repeated cycling of readout and feedback. And that's how you generate logical qubits from physical qubits. It's really a dynamic process. And for that, you really need low latency readout. For the instantiation, there is an advantage to doing readout fast enough, because if your readout is very slow, by the time you've exposed the camera and you transferred all the pixels and you made your decision. If all this is very slow, you will have lost atoms on the way. These atoms that you place in this static trap, they have a lifetime of a mean lifetime of typically tens of seconds, can go up to many hundreds. But if you have many of them, there's a non-negligible probability that you will lose a few if you take too much time imaging. And so in the end, if your imaging is too slow, it will limit the amount of atoms that you can eventually have, the amount of qubits. So that's also important. So let's focus in on readout. So we've already, so the quantum machines provides several systems to do readout for optically addressed qubits, and this seminar revolves around the observe unit, which is a device that sits in between a camera, in this case the Hamamatsu camera, the QCMOS, and our controllers, the OPX controllers. And what happens here is that the OPX, the controller, triggers the camera, because we've typically ran a sequence of gates in before on the qubits, and now it's time to read them out. So we send a trigger to the camera takes a picture, transfers the pixels to the observe. The observe then performs real-time image processing. The observe is also an FPGA-based system, performs real-time image processing and extracts what's known as the occupation matrix, which is basically a Boolean matrix with ones and zeros to represent whether there is or isn't an atom there. So the way readout is done for atoms and ions is that you map the internal state of the qubit, the internal state of the atom, on whether you see it or not in a picture. The way it's done is there are two levels for the atom, the two computational levels, 0 and 1, and you couple only one of the two, typically 1, to some higher level with some laser. So there is a resonant transition between the one state and some other level. And so now if the atom is in the one state, it will fluoresce, it will absorb and emit photons in this cycling transition, and you will see it on the camera. It will fluoresce photons. If you are in the 0 state, it will be dark. You will be too far off resonance to this cycling transition, and you will not scatter photons, and you will not be visible on the camera. So basically, by driving this transition and taking a picture, you map the internal state of the atoms on whether you see it or not. So if you don't see an atom, it's not that he's not necessarily there. He's typically there. He's just dark to the imaging. And if you do see it, you know that he's in the one state. And so reading out qubits, atom and ion qubits, is always this game of looking at a region where an atom should be, counting pixels and summing pixels and seeing if it crosses a certain threshold. And so this is what the observe does. Takes the raw pixels and then goes atom by atom and discerns whether the atom is there or not, and then sends the occupation matrix, basically the position, the existence, the state of the atom to the OPX. In the initial instantiation phase, where you just throw in atoms and you take an image, there's no mapping of the internal state. There you really just image if the existence of an atom, and their readout is only done in order to be able to tightly pack atoms into a tight array. We also have other instruments to read out single photon detectors and so on, and these are all scalable solutions, but the focus of this discussion is really the observe module and how it links Hamamatsu cameras with the rest of our control stack. Let me move to my next slide. So yeah, delving a little bit deeper on instantiation, since this is something that we've been doing for a while, and this is kind of the background of recent results that we have with the Hamamatsu. As I said before, so we've done this already with Mark Safman. That's the first demonstration we ever done. We have since done it on numerous occasions, and here we can see that we've tightly arranged a 7x7 atom array in various shapes and forms. This is all decided by the user, and we synthesize these RF signals that are sent to these dynamical tweezers in order to divert these laser beams. And so basically these waveforms that you see here, these are generated by the OPX, by the quantum machines controller, in order to steer laser beams and move atoms. So here the sequence is as before. but we've done these things with EMCCD cameras, where the latency to transfer pixels was much longer than with the Hamamatsu, which we will see in a moment. And that meant that the whole latency from the moment the exposure was started on the camera to the first moment we could respond was on the order of more than 20 milliseconds, on the order of 20 milliseconds, which is not bad if all you want to do is arrangement, but for mid-circuit operations, this is a bit too long, because it starts to be a non-negligible percentage of the coherence time of these atoms. And so just to break down all the latency, we typically start counting latency from our point of view, from quantum machines point of view, after the pixels have arrived to the camera, after the exposure time ended, because how long you expose the atoms to your fluorescing light depends on the kind of atom you have, how your optics, what the collection efficiency, what wavelengths you're working at, and so on. And so that varies greatly from anything from 0.5 milliseconds to 300 milliseconds or so, which we will see actually in the next point. But this is a bit out of scope for this discussion, because because that's something that is continuously being improved. It really has to do with the physics of the atoms and the engineering of your optical system, and there are many paths towards reducing this time. And it's outside of the scope also of us, the Hamamatsu and quantum machines, where we only make the camera and the control equipment. So the moment the camera has exposed and has the pixels, then the first limiting time scale to do feedback is how long does it take to transfer the pixels from the camera to some processor that does image processing, because I need to do image processing to know if an atom is there or not. And so we've benchmarked most of the cameras that are being used in academic environments and also in industry. And we see that EMCCD cameras are on the order of 30 to 35 microseconds per row of pixels. So typical regions in experiments, in atom array experiments, require about 500 rows of pixels. 512 is the size of a typical sensor. You can do half that, but that's a very reasonable number. So 512 rows of pixels at this rate will take between 15 and 17 milliseconds just to transfer the pixels. And that already quite a large penalty in terms of latency, because this is already on the order of 5 or 10% of the coherence time of the atoms. And so it's just too much. Typically, we say that the time scale is negligible if it's below 1% of the coherence time of an atom, which can be many hundreds of milliseconds, but here still 17 milliseconds is a bit too much. And then we also need to do image processing. Now we do the residual latency of this image processing is actually not that much, because the pixel anyway arrive to our observe unit row by row. So the pixels arrive. Pixel rows arrive one after the other, and the observer is smart enough to know that he can already start doing image processing the moment he received all the pixel rows. If he already received all the rows of a single line of atoms, he can already start doing the image processing, and he doesn't have to wait for all the frame to arrive. And so by doing that, basically the residual latency of the image processing is only that of the last row of atoms. And so typically on the order of a few tens of microseconds. And then the occupation matrix, after you've discerned the position of every atom, the occupation matrix is sent to the OPX, to the controller, that then can then send the feedback pulse, and that takes 32 nanoseconds per atom. So even for 1,000 atoms, that would be less than 40 microseconds, and typically totally negligible compared to all other time scales. So then you have your occupation matrix inside your controller, and now you are free to develop whatever real-time sorting algorithm or quantum error correction sequence that you want, because you have read out the state of the atoms now. And that there's a large variance, very simple atom arrangement that we give for free. You can find it on our GitHub. Takes about 15 microseconds. And people do more fancy atom sorting algorithms that can take up to several hundred microseconds. But it's always in this range. It's always a few hundred microseconds at most. And then once you, and this is to make the decision of basically which signal to output, some algorithmics of that. And then when it's time to actually synthesize the signal and play it, this is something that we really excel at. We can typically do that within less than a microsecond or a few microseconds at most, because of the fact that we have all these numerical oscillators on the pulse processor, we can synthesize these chirping waveforms on the fly. We can just steer this numerical oscillator left and right and ramp them in power up and down without having to synthesize a waveform sample by sample, as it's sometimes done using other techniques. And that part, just the synthesis of the signal, in other architecture can take many milliseconds and is comparable actually to the pixel transfer time. Whereas here with quantum machines, once you had the pixels, basically it's a matter of a few hundred microseconds before the first sample out of the DAC comes out and you can do feedback. And so so this was the situation up to a few months ago, and then we've benchmarked the Hamamatsu, we've integrated it with the Observe, and we really do see that we cut down the pixel transfer rate by an order of magnitude to about 3.6 microsecond per row of pixels. And to demonstrate that, we've done this demonstration at the Max Planck with the help of the Johannes Zeyer group, part of the Emanuel Bloch group, and with the great help of Alex Kotikov from QM that worked very hard on making this integration happen. And here we have the whole timeline of the experiment, where we only did atom arrangement, and even at that we still have some work to do to optimize. There are still some defects because we're trying a fancy atom arrangement algorithm and not the standard one, but that's besides the point. We did verify that the pixels that we received were the correct ones and that the occupation matrix is the correct one, and we've managed to benchmark the latency. So indeed, to transfer 1024 pixel rows, it took 3.68 milliseconds. So 1024 pixel rows is quite a lot of rows. As you see here, there was even not really a need to expose this whole region of the sensor. We could have zoomed in and save us almost about a factor of 2, but this was all done in debugging mode. So, but we recovered this 3.6 microsecond per row of pixels as expected by the specification of the camera. So we were very happy with that. That means that if we can do things with 100 rows of pixels, as the look-in paper was using, we could hope to have this pixel go down to a few hundred microseconds, which is really great. And then image processing on these 399 sites, the total sites, was about 184 microseconds. We have not yet implemented this row by row image processing on the Hamamatsu yet, but we will. And when we will do that, this will probably go down by an order of magnitude to below 20 microseconds or so. So this will be even smaller. And then to transfer the occupation matrix, as I said, 32 nanoseconds per atom. That comes up for 399 sites per site, sorry. This comes down to about 12.75 microseconds, so quite negligible. And the real-time algorithm, the sorting algorithm, was another 113 microseconds, and then the first sample of the DAC came out. So we can see that really from the moment we finished the exposure, which in this case was very long, they're using strontium atoms, which have a very narrow line width, so it takes a bit longer to image. And again, these are issues with that people are working on, and these times will go down. But from the moment we've finished exposure to the first sample out of the DAC, we're talking about a few milliseconds, where really the amount of pixel we could really save on that by at least a factor of 2 and drop everything to a millisecond or so. So really winning at least an order of magnitude compared to the feedback latencies that we were used to. And so we are very hopeful that with the Hamamatsu camera and with quantum machines equipment, we will be able to go deeper and demonstrate milestones of quantum error correction using atoms and ions, something that we are already underway with several partners. So if you have any questions, and if you're interested in our systems, in quantum machine systems to drive atoms and ions or optically addressed qubits in general, please don't hesitate to contact me. We will see together these systems that we're building are tailored to your needs. Don't hesitate to contact me at Ramon at Quantum Machines if you want, or just through the seminar somehow. and we can sit together and build kind of a system for you that will allow you to do mid-circuit operations. So with that, I thank you, and I pass the microphone to Sebastian.
Yeah, thanks, Ramon. Give me a second, and let's try to interface to my screen, which I hope should be visible right now. Great. So in any case, thanks, Ramon, for explaining all the details about the operational parts of the imaging and the readout during quantum computing operations with neutral atoms or ions. And now I do have the pleasure to explain a little bit in the coming 10 minutes about the hardware behind the whole topic, our new Orca Quest, or the latest iteration of that, the Orca Quest 2. So when we talk about, detectors, it's actually only a few parameters. It's either sensitivity, speed, which kind of goes hand in hand with sensitivity, and in the end, field of view. And Ramon already mentioned the speed improvements to some degree. I'd like to put that a little bit into perspective to EMCCDs alongside the sensitivity, and then with one application example at the end. The sensitivity of cameras, especially of CMOS cameras, is typically described by simply two parameters, which you can see here from a manual. On the one hand, it's the quantum efficiency, which is the conversion efficiency from photons to photoelectrons, and the readout noise, which is the uncertainty in the determination of the magnitude of photoelectrons one had with at the beginning. Looking at the quantum efficiency of the camera directly to the signal levels of different neutral atom species or ion species, we can see that, well, especially for ytterbium, strontium, and calcium to barium, we're very much close to the optimum of the camera. But also in the blue, it's not too bad. And that was actually a major improvement from the Quest 1 to the Quest 2. In that sort that the UV sensitivity was massively improved, which is kind of a big advancement for ytterbium, beryllium, and magnesium without any compromises in the other spectral ranges. Readout noise, as mentioned, is the level of uncertainty we'll have while determining our photoelectron levels. And this is pretty low with the Orca Quest, which in the end is achieved without any electron multiplication, contrary to EMCCDs, which I'm going to cover in a second. The advantage of not using electron multiplication is that if we observe the output probabilities of a single pixel under a given signal, in this example, under complete darkness, then we'll simply see a Gaussian output probability. And if we change that signal level of the pixel to higher intensities, just like, for example, to 1 photoelectron, 2 photoelectron, 3 photoelectrons, stuff like that, we see that the offset changes, but the spread, the shape of the Gaussian doesn't change, meaning the noise of the camera is independent of the signal level. And that is a great advantage because it gives us a great intensity resolution. And what I really appreciate is that this is not only exclusively visible in nice calculations of some Gaussians, but we can see it directly in the histograms of the images. So here as a small stupid example, I've taken a photograph with an Orca Quest of my coffee mug. I actually used an OD6 filter to reduce the light intensity down to the single photon level or to the few photon level. And if I observe the histogram on the right side of the image, we can directly see that it's kind of non-continuous, that we can see the discrete nature of the photoelectrons, which is inherently proof that we're operating at the physical limits of light detection. If we compare that to the operation of EMCCDs, I mean, I somehow need to put that into reference, and EMCCDs have been the technological reference, but their operation parameter is, or their operation principle is very different. So it's very hard to put that into direct perspective. But the noise of EMCCDs, and especially the readout noise, it's basically absent in dark conditions if the gain is high enough. So if we work with our output probabilities again at the end of the CCD register, then we see if we don't have any photoelectrons, we have a very, very narrow distribution peak. However, if we add one photoelectron to our pixel and at an EM gain of, let's say, 1000, then we get an extremely broad distribution. We could generate 1000 or maybe even 4000 electrons. And that distribution even broadens the more signal I'm inputting into the multiplicative register. What that essentially means is that the noise without any signal in absolute darkness is very narrow, but as soon as we add some light, we'll broaden the distribution and we'll add so-called multiplicative noise or excess noise. Now, what we typically do to benchmark cameras is we kind of observe how much signal to noise ratio they could generate under the assumption of Poissonian distributed light, just like including all the factors like quantum efficiency, dark current, excess noise, and of course, readout noise. And if we benchmark here the EMCCD against the Quest in its fast mode, which has kind of a fairly high noise for the Quest, then we see that as soon as we get an average signal higher than, let's be critical here, higher than 0.3 photons per pixel per readout, then we're better off in terms of signal to noise with the Orca Quest than with an EMCCD. On the contrary, if we, for example, observe the point with the Orca Quest at a signal level of 10 photons per pixel per readout, to achieve the same signal to noise ratio with an EMCCD, we would roughly need double the amount of photons, which of course would then mean, well, either double the exposure time or double the excitation power, both situations which might not be favorable in every situation. Talking about speed, which has been mentioned by Ramon, actually the virtual 3.6 microseconds per line are the physical readout speed of the camera. In the end, if we're driving that at the full field of view, it comes down to 120 frames per second, or a readout time of roughly 8 milliseconds for a full frame of 9 megapixel for 2304 rows. In the end, in a CMOS camera, that scales with the number of rows, contrary to an EMCCD camera or a CCD camera in general, where it scales with the number of pixels. A CMOS camera is parallelized into one direction. So again, benchmarking the speeds against each other is not a straightforward task, but I went down the route to just take the frame rate of comparable field of views. And here we see if the field of views are extremely small, just like 32 by 32 pixels, still the Quest gives us half the readout time, or at least half the readout time, double the readout speed. If we zoom a little bit in onto larger field of views, here, as Ramon mentioned, in the field of view of 512 by 512 pixels, we're by a factor, well, I'd say this is 5 to 6 faster than EMCCDs. And larger field of views typically can't be generated by EMCCDs because the most common chips actually only have a size of 512 by 512. Putting all of this together, I've taken one figure out of a fairly recent publication where they managed to perform the mid-circuit readout and control below 1 millisecond. As Ramon mentioned, those operations have to be fast to be within the coherence time of the atoms. And if we observe here under figure D, the timing diagram, then we can see out of those 1 millisecond, roughly 700 microseconds are related towards the camera, which is on the one hand local imaging, which is simply the exposure time, which of course can be shortened or enlarged, but it's kind of fit towards the case that we can make the discrete distinction and a high fidelity distinction between on or off. But of course, if the camera is more sensitive, then we could shorten that time. The camera readout here for this application happens within 200 microseconds, and they wrote that they read out 24 rows of pixels. By the image here on number A, I judged that they had maybe a width of 100 to 150 pixels. So such a readout with an EMCCD alone would have taken longer than 1 millisecond. So this readout time is at the moment likely only possible with the Orca Quest. Concluding all the stories, when we talk about sensitivity, I'd like to describe some sensitivity margin. What is the technical signal-to-noise ratio or exposure time or laser power we lose because our cameras are not absolutely perfect? And interestingly, in the blue-green region, it's not really much. They were basically operating at the physical borders. Even if we had 100% quantum efficiency and absolutely no readout noise, we could only reduce our exposure time by 10% to achieve the same signal-to-noise ratio. In the infrared, for rubidium atoms, for example, it looks a little bit different, but of course we're working on that. Readout speed, hard to benchmark, but at least there's a factor of 2 between EMCCD, but it very much depends on the scenario. Typically, it's way higher because of being parallelized into one dimension. And finally, field of view, 9.4 megapixel are roughly 20 times the pixel count to typical EMCCDs, while we generally wouldn't need all of them in quantum computing applications. So it's good to have them to be flexible for future scaling up. And with that, I thank everybody very much for your attention, and I guess I'll open the floor to the Q&A session, if that's fine, Rob.
Yeah, absolutely, no problem at all. Thanks very much, both of you, for giving those presentations. We do have a few questions that have come in, and I'm sure there will be a few more as we are asking these as well. If you guys have the, and I'm saying that to Ramon and Sebastian, if you've got the questions field open, you'll be able to also see the questions that I've been presented with as well. So the first one I'm going to put, it looks like it's probably going to be to Sebastian. Does the speed and sensitivity comparison imply that EMCCDs are obsolete today?
So that's a strong statement. We've only managed to test the EMCCD sensors that are on the market. There's no reason that I know of why somebody can't maybe invent an EMCCD-based camera, that is faster for some reason. Although there seems to be some physics behind the reason why EMCCDs are so slow. You need to refresh and so on. But these speeds, yes, transferring pixels in 20 milliseconds is probably too slow to allow quantum error correction. It's just too large of a fraction of the coherence time, and also too much of a multiple of the gate time to extract entropy, to extract noise quickly enough from qubits. Yeah.
If I might shortly comment on that, if we're talking under the boundary conditions of the applications Ramon and me described, just like imaging of small dots in arrays with a photon number, where you want to reduce basically the number of photons as much as possible, but also want to be as fast as possible. I would say yes, under the assumption that you're kind of flexible with the rest of your setup. For other applications, it might not be the case. I think EMCCDs will stick around for a while, even though we see a gradual replacement of CMOS technologies, of CCD technology.
Okay, and also we've got another question here. Is it rolling or global? Rolling or global shutter camera?
Rolling. That's basically incorporated in the readout times I've shown in the schematic from the mid-circuit readout, and that's basically included in the latencies Ramon discussed. Essentially, it is the 3.6 microseconds per line.
Okay. We've got quite a few coming in now, actually. So also, we've got one here. Are the current feedback latencies achieved with Hamamatsu camera and QM equipment enough to enable quantum error correction?
Ramon, I guess that.
Sorry, the question about the rolling shutters, or we moved on?
Oh no, sorry. We could carry on with the rolling
questions. The question about are the current feedback latencies enough for quantum? Yeah, so well, quantum error correction is a lot of things, and not everything was demonstrated yet. But for example, the Misha Lukin paper that both me and Sebastian showed was not done with QM equipment, but it was done with Hamamatsu cameras, and they had a very limited kind of mid-circuit logical capability. Their controller was kind of a DIY. You could do all that and more with the QM controllers in terms of latencies, and then you could generate logical states, protected, and so on. There's other compute that needs to be done, real-time compute that needs to be done as part of quantum error correction, which is out of scope here. You need to decode the quantum state, and so there are other latencies involved. But the quantum error correction demonstrations that are currently being showed, yes, that these latencies are sufficient. I mean, also you see the latency is still, even in the state of the art, the best system currently available in terms of latency in the world today. More than half of the latency is still exposure time. It's still just collecting photons, and only half is everything else, is transferring pixels and doing kind of calculations. And also, yes, we're already in a regime where quantum error correction is possible with these latencies.
Sebastian, have you got any comments on that, or shall I move on to the next question?
No, I think that's more for Ramon. I think that's fine with me.
Okay. Let me just see here. So there is a question here that asks about, you mentioned sensitivity margins in your conclusion. Could you explain again what you mean by sensitivity margin? What did the 2.5 by 800 nanometers mean?
So yeah, theoretically, you can calculate which signal to noise ratio is possible under which signal with a given quantum efficiency and a given readout noise. Now, if I compare that one to the perfect one, say with a camera with 100% quantum efficiency and 0 readout noise, then I get a difference, and that's the difference in signal to noise ratio, the difference in image performance, discrimination fidelity in terms of ions I'm seeing at the end. And that's kind of what's important. If we go back to the 800 nanometer example, I think at 800 nanometer, the Quest has a quantum efficiency of roughly 50%, meaning we still can improve a lot on that. But when we're talking at peak quantum efficiency wavelength, 85% at, if I remember correctly, that was at roughly 500 nanometers. Ramon, that should be strontium wavelengths. Is that correct?
Yes, could be. Depends.
But the details don't matter here. If we're operating at those fields, and if we benchmark that against absolute perfect camera, then we see the difference is really not striking. We could get the same result with a Quest by a 10% longer exposure time. Yes, 10% is something, but it's not dimensions far away. At 800 nanometers, we still could reduce the exposure time by a factor of 2.5 if we were to double the quantum efficiency. That's what I meant by sensitivity margin, just like how much room is there still for improving the sensitivity.
Okay.
Hope that makes it clear.
Ramon, did you have anything to input into that one before I move on to the next question?
No, so reducing the exposure time is of course very important, but there are many projects attempting to do that, especially for atoms that have already a very long exposure time. So 10%, people are trying typically to like reduce that by a factor, and so 10% is, I think, something that isn't a big issue. But
in the end, what I meant by that is just like purely by improving the camera performance, there's simply no order of magnitude in store anymore, because we're always we're basically gathering everything there is, every information there is. So meaning from that perspective, we have to make the improvements more on the, well, illumination scheme, trapping scheme, just like that we don't kick the atoms out, and so on and so forth.
Exactly.
Okay, we've probably got time for 2 more questions if I can squeeze those in. So, and I'll put this to both of you. Could you explain in depth why the readout speed of QCMOS is faster than EMCCD in the case of row by row readout?
May I go first, Ramon?
Yeah.
The simple reason is parallelization. So just like in a CCD, we do have a serial readout, and each pixel is read out sequentially, whereas in a CMOS camera, and then typically the implementations of the general scientific CMOS cameras, which is also part of the QCMOS cameras, each row has its row of ADCs, meaning each row is digitized in parallel, which takes exactly 3.6. Actually, it's 7.2 for 2 rows in parallel, but those are details that don't matter here. In the end, if we digitize a whole row of the QCMOS, which is, if I remember correctly, 4096 pixels long, it's exactly the same duration as if we digitize the row at the length of 100. Whereas with an EMCCD or a CCD in general, that would be a serial readout. That would take way longer, especially the longer the rows get.
Yes, nothing to add.
Okay.
Thanks.
We might be able to squeeze another one in as well then. So I think, Ramon, this is probably targeted to you. Slide 15, does the number of pixels on the EMCCD camera limit the number of atoms or qubits that can be imaged? In other words, what is the average mapping of atoms to pixels?
So we see there's quite some variance. It depends on the magnification, of course, but let's say on the small side, if you're hoping to squeeze as many as you want, so you need to count. So you see sometimes setups with only like 4 pixels per atom, 2 by 2. But then you need to also count the pixels to the adjacent atoms. There's some space in between. You need to precisely place them at a precise distance, because that sets kind of the interaction between them. And so if you count that every atom takes about 10 by 10 pixels, then you see that with a 512 by 512, you have a room to put around 2000 atoms, which is quite a big system today, 2000 atoms, but already surpassed. And I think in the future, people are really aiming for this 10,000 atom holy grail. So I think there might be an issue with doing many thousands or 10,000 atoms if you have only 512 by 512. Yeah, unless you can, shrink things, but then you will affect other parts of the physics. So.
I mean, just like commenting on that, commenting on the imaging side, we're not really doing an imaging situation here. We're reading out. So we just like, as we mentioned often, we just want to know on off. So we don't need to know the shape of what we're actually seeing as a point spread function. We just want to know on off, and therefore theoretically we don't even need any spatial resolution. So in the extreme case, we could map one atom on 1 pixel, one atom in between, and one atom on 1 pixel. Even though I think that's a very hypothetical approach, because I'd imagine such a system to be extreme hellish to align.
Yes, and also the spacing between atoms is larger than the size of an atom, so it's a bit less than that. But yes, I agree with what you say.
Okay. Well, we are just about up on the hour now, so I am going to wrap up the questions there. If anyone had a question that they've asked that either of our presenters haven't been able to answer for you right now, don't worry. All the questions are stored, and someone from Quantum Machines or Hamamatsu will get back to you directly. Also, this entire webinar has been recorded, and the video recording will be available on the optics.org website in about 24 hours or so. What I'd like to do is finally thank all of our attendees for coming along to watch the presentation, and also thank you to Ramon and Sebastian for giving us a great insight into a very exciting technology. Thank you very much, guys.
Thank you.
Thank you.
Have a good day.
Have a very good afternoon, everybody.
You too.
Bye.
Bye-bye.